let's get going. Week 18, day 1. Your mods are going to be due at the end of the semester. And there's not going to be a final or anything for that, so that's nice. Cool. Dalin, Lave, Vacalar, do you guys have something to show us for the Unreal Engine assignment? Alright, get them done. Alright, so our topic for today is shaders. So, a shader is a program that runs inside of your GPU, basically. And there's all sorts of really cool things you do with shaders. For example, if you took a 3D model like that and you wanted to render it, pay no attention to the center top image. If you wanted to render it, if you wanted to render it like it was a cartoon, then you could do what's called cell shading. So we've talked a little bit about lighting and things like that. So if we zoom in on this, this is using quads instead of triangles. The principle is the same. There's a light source kind of in this direction here. The normal vector of the surface is this, right? It's a line coming out of the perpendicular to the surface of a model, and if the normal vector is pointed at the light, then it gets fully lit. If it's pointed a little bit off to the side, it gets less lit, and if it's pointed away from it, it gets not lit. There's probably some ambient lighting in here to make sure it's not black. And this looks like a 3D thing. And a lot of times when we're talking about doing cartoony stuff, for example, one of my friends, Nate Beal, is playing a lot of Genshin Impact these days. You know, fairly beautiful world, fairly nice world. It looks like a cartoon though, right? So, hand animating cartoons is really it's expensive and time consuming, and you don't get a lot of flexibility with it. So an approach that a lot of games take is they render all this in 3D, and then they use a shader to turn it into something that looks like it's 2D. And so over here you can see that's really 3D there. But like this guy's cape here, even though it's being rendered in 3D, it looks like it's a cell, animation kind of thing. Any of you guys play Genshin Impact out of curiosity? I tried playing it and I was just bored out of my mind. I don't know what to say. Like, it was beautiful. I think it was just the running speed was too slow. Might have been the problem. Like, I was just like I had to walk like over this way and go up to the top, and I literally logged out because it took so long to just walk across the bridge and walk up through the town and walk up that way. I'm like, no, I'm done. I just Alt F4'd out of it. I don't know. I just can't stand games, I guess, that waste my time like that. Beautiful though, beautiful game. And so again, you see this is probably skeletal mesh, the person sitting down, but it's rendered as if it was 2D artwork. All the flowers here are rendered. These are probably sprites maybe on top of it. And so that's done using something called a shader. Had a very Breath of the Wild feel to it. Yeah, I think that was deliberate, especially like there were climbing parts in the game and things like that that were like straight out of Breath of the Wild. I don't know, teleport spots. Yeah, I don't know. Just like I said, the movement speed being so slow just like killed me. I just like, I just can't deal with it. Okay, so like in Breath of the Wild, you could run jump off a hillside, hang glide, slide on your shield. Like there are a lot of ways of moving quickly through Breath of the Wild. Maybe I didn't get that far in the game. Okay, so here we have a 3D model, and a lot of times we don't want a 3D model to actually look like a 3D model because it's very jarring. If you've ever seen some Disney animations where they have tried doing 3D, like it looks kind of bad sometimes, right? Like not Pixar. Isn't that a span or something? This logo. Yeah, they a lot of times when Disney tries doing like 3D stuff, like it, yeah, just I don't know. Like the 2D stuff looks better. Anyway, so how do you do that with cell shading? Well, take a look at this. So rather than drawing like a smooth surface, what you have first of all is you have the outline of the thing drawn in black, right? You see that? So the very outer edges are drawn in black. And you can do that in a number of different ways. A very easy way of telling is if a point is inside and then a point is outside, you draw a line there, right? So, or you do what's called the convex hull of the thing and basically wrap it in a thing that wraps the whole thing. You do 2D convex hull, which would give you the outline of it. Here it's doing internal lines as well, so it's probably got some sort of system for that. Maybe this, it might be just done manually as well. This is a sprite, so you can see there's a square there where the sprite gets drawn in. On top of it, a sprite is a 2D picture. Okay, but let's look at the shading on this. So all of this stuff, it's actually curved belly, right? But here you don't see any of that curve. All of that gets erased. And so what they do is they basically say if the lighting is like pretty good, just draw it as yellow. And if the lighting is like kind of bad, draw it as like a darker yellow. And for the orange, you can see there is 1, 2, 3 colors of oranges. And so they just basically have an if statement saying like based on how much light you have, if the lighting is above 80%, draw this shiny color here. There might actually be another one. Let's see. Looks like there might actually be an even brighter point here. It's kind of hard to tell. So basically if the lighting is above 80, draw this shade. If it's above 60, draw this shade. If it's above 40, draw this shade. And if it's below 40, draw this shade. Something like that. You just have thresholds and you just have colors. And so just everything with that amount of lighting becomes orange. Everything with this amount of lighting becomes dark orange. Everything with this amount of lighting becomes yellow orange. And so it essentially removes all of the 3D features of something and makes it look like it's 2D. It's pretty easy. So you can use what's called, classic. That might have been, in fact, been one of the first games to do cell shading. I don't know. It's a little exaggerated for me. So yeah, does a contour to get the outline of it, and then it flattens the colors, and yeah. So Breath of the Wild. That's what it looks like if cell shading was turned off. That's interesting. So that's what Breath of the Wild normally looks like. So you can see that just areas that are well lit are one color and then are a darker color. But this is the actual 3D model. This is what the game would look like if it wasn't cell shaded. You can see that even though there's more detail on it, right? You can pick out the nostrils and the more bits of hair. It actually kind of looks worse. It looks like something out of the N64 era. Lobbies, you. Yeah, like you can literally see like there's more detail in this. But it just doesn't. It's not a good look, right? And so Breath of the Wild's aesthetic Breath of the Wild can actually load Wii U Mii's. That's funny. You know, and so basically, it's you're actually throwing away data to do cell shading. It's specular reflection is the shiny bits, two-tone shading, so you can see like on his shirt there's just two colors there. Rim lighting makes the edges look a little nicer. It looks so bad. It looks so bad. Goodness. So, going back to our topic for today is shaders. And so a shader is a program that runs on your GPU. And they're a lot more limited than like a full-on program. Does it save on resources if it's cell shaded? Not really, because you're still. I mean, I guess you don't have to spend as much of your art budget on. Like you saw how bad Link looked, you know, with the cell shading turned off. Like you don't have to spend your art budget like cleaning that up. So cell shading will hide a lot of flaws. But essentially, in terms of performance, you're still rendering the same thing, right? You just have a shader running at the end of it that is going to flatten the colors, essentially. This looks pretty nice. Okay, so might be a little bit too complicated to go through. So we get some simpler ones. Okay, so there's two different kinds of shaders. There's what are called pixel or fragment shaders, and there are things called vertex shaders. And so a fragment shader is a pixel shader. Basically, what it means is if you have just a one-to-one mapping of pixels and fragments, they're literally the same thing. But you could feasibly be rendering more fragments than there are pixels on the screen. Like if you're going to be doing super sampling kind of thing, where you've got like 4 pixels rendered for every pixel, so you do anti-aliasing nicely. So, yeah, this will be a nice thing. So, let's say that you've got a triangle, right? And you've got green, red, and blue, and you need to rasterize it. What rasterizing means is you take all of the pixels and kind of push them onto the screen. So the screen is a big 2D array of pixels, right? And so if you've got a triangle that are covering these here, at some point you need to go from like I've got a triangle and some data structure to like actually writing every pixel to the screen. This pixel is red, this pixel is green, this pixel is blue, and that's called rasterization. Rasterization means taking a shape and coming up with what 2D pixels, like what pixels go onto the screen. And this looks like a meme setup, is it? I don't know. And so how that happens is kind of interesting. We talk maybe more about it in 50B, but I guess I can go over it a little bit here. We've got a bunch of triangles in the world, right? And so let's say that you've got this will kind of reveal to you guys what rasterization is about. New page. So let's say you've got a screen. Pixel pixel 0, 0 is always the top left corner. And you've got some triangle that you want to draw on the screen. This triangle is 5 units away. You've got some other triangle you want to draw to the screen. And this triangle is 2 units away from the camera. Which one's going to draw? Which one's going to appear? If you've got one triangle that's 2 meters away, one triangle that's 5 meters away, which one's going to be on top? The rainbow one that's 5 away, or the purple one that is 2 meters away? What do you guys think? Which one should appear on top of the other one? We're down to 4 students in this class. So depressing. It's games. Don't you want to know how games work? This is how 3D games work. It's like, it's cool to me. End of the semester burnout, I guess. All you guys got left are your projects. So, is this going to be on the final? There is no final. Just learn. Just learn. If you want to go, into games, this is you got to know how this thing works, or you're going to look real dumb in the job interview. You know? I'm really, really, really nervous. Okay. About which triangle's in first, or about the projects? Sampled sounds for the project. Okay. All right. They're really cool sci-fi. Right. There's no reason to be nervous, then. That's the hard part, right? You just need to put them in. And if you want help putting them in, I can help you. It's kind of straightforward. Yeah. So yeah, Lave has it. The 2 is going to draw on top, right? It's gonna all be purple. Right? And so the way that works is there's something called a Z buffer. And this is one of those things, like, if you haven't heard of it, like, you're not going to get hired as a game developer. Every time you rasterize something to the screen, not only do you write each individual pixel, like this pixel, this pixel, this pixel, this pixel, this pixel, and their color, you have what's called a screen buffer. A screen buffer is a 2D array of colors. And that basically holds, this one's going to hold red, this one's going to hold green, this one's going to hold blue. Not only is it just a 2D array of pixels, we've also got something called a Z buffer. And so the Z buffer holds the depth, how far away that pixel is. If I'm trying to render purple, and I then come over and with the rasterization, what you just basically do is you just iterate over this square here. Is it in the triangle? Is it in the triangle? Is it in the triangle? No, 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 no. Oh, it is. Draw purple. Is it in the triangle? Is it in the triangle? Is it in the triangle? And you just loop over the whole thing. And if it's inside of the triangle, and you can tell if something is inside of the triangle by using cross product. So if you want to tell if something's inside of a triangle, you've got a line there, and you got a point here, and you want to see if the point's inside of it. Cross product will tell you, yep, it's to the right. You've got this line here. Yep, it's to the right. You've got this line here. Yep, it's to the right. Okay, congratulations, it's inside the triangle. So if you take 3 cross products, that will tell you, yes, it is inside of the triangle. And if you do over here, then this cross product tells you, nope, it's outside, and it doesn't draw. So basically, you just loop over a square containing the min and max of the triangle. You just go over the whole thing, and anything that's inside, draw purple, draw purple, draw purple. But you also write down how far away that point is from the camera. So all of these are going to write into the Z buffer. They are 2 meters away. And then when this triangle here rasterizes, it's going to draw the yellows and the greens and the reds and the blues. When it gets here, it says draw blue to this spot right here. Draw some rainbow colored thing right here. And the Z buffer says, no, you're drawing something that's further away from something that already exists. Hide it. And it will stay purple. Now, if I were to draw a third triangle on here, if I was to rasterize a third triangle that was, let's say, white, and we do this, and this was only 1 away, then all these points here, when you try rendering it, I'm trying to draw something a meter away. There's something in there that's 2 meters away, 1 meter is closer. And so the 1 will overlap the 2, which will overlap the 5. And of course, every point can actually be a different distance away, and so it actually interpolates between, depending on where the triangle is in space, Like this edge here might be 1,000 meters away, and this one might be 5, you know, and so it'll do some sort of interpolation. This is 500 away here, or something like that. But that's the basic point. When you rasterize it, you just loop over every pixel within the triangle. You draw it to the screen buffer, and you draw it to the Z buffer. And if the Z buffer has something there already, then the Z buffer holds which one's closer, which one's further away. Okay. You guys understand this concept? So rasterizing means just taking a triangle and turning it into pixels that go on the screen. Cool, that's rasterizing. And your game engine is going to spend a lot of time trying to do this as little as possible, right? If you've got a billion triangles in the screen, you don't want to spend, ain't nobody got time for that, you know? Like overdrawing the same spot over and over again. No. So what a game engine will do is it'll do everything in its power to try to not draw as many triangles as possible. Right? So it uses like the visibility tests, the visibility calculations. It'll use backface culling. If a triangle is facing away from you, it won't draw it. If you know that if you're inside of a room here, you can't see anything in the room over there, all those triangles don't get drawn at all. And so there's a lot of research and a lot of activity in trying to optimize that process so you can have a nice looking world, but at the same time, you don't have to draw that many triangles. Okay. So voxels are basically 3D cubes, right? And so, yeah, Minecraft, right? It's a different pipeline than the rasterization pipeline, but at a certain point, you have to put pixels on the screen, right? Okay, and there's some games that don't use Z buffers at all. For example, if you can make it so that this triangle is drawn first, and this triangle is the purple one's drawn second, and the white one is drawn third, you don't have to do the Z buffer test at all. You just draw the 5 first, then the 2 second, then the 1 third. That's called the painter's algorithm. Because when you paint something, you paint your back layer first, and then you overpaint it with the higher priority paint, and then you paint that over with a higher priority paint if you want to. And so that way you don't need a Z buffer. And in fact, when the Z buffer was first proposed, it was laughed at being an impractical waste of memory. It would take a megabyte of RAM in order to implement a Z buffer. You can't have a float for every pixel on the screen. What are you, crazy? So yeah, it was originally mentioned just as something that nobody would ever do because it is way too expensive in terms of RAM. That was back in the 70s, and there was a real breakthrough in RAM actually in the 70s, and the price of RAM started dropping precipitously through the 80s and 90s, and now RAM is so cheap we don't even worry about it too much these days, you know. But back then, you're talking like $1,000 a kilobyte of RAM, right? So you're gonna spend like a megabyte. No, nobody's got memory for that. Nobody's got money for that, you know. So okay, so that's rasterization. Okay, so a Vertex Shader can do things. It's a program that can actually like move the vertices around, things like that. So you can do things that look really cool. Let's see here. Right. So you can like write a program that moves the vertices around, and looks pretty rad. You know, it's a neat look. The Fairchild has 64 bytes of RAM. Yeah. So yeah, it's pretty cool. Vertex shaders are neat. Let's see if there's any other cool things I can show you guys. Ooh, yeah, if you guys are serious about game development, by the way, there's a lot of really good GDC talks that you can watch for free, and they just have them up on the GDC channel. Let me link that to you guys, because that's honestly, like, if you want to learn like advanced game development stuff, this is the best resource I've ever found. Let me put that on there for you. I've spent hours just watching postmortems and things like that. The inventor of Diablo talking about the process. Look at that. That's really cool. Yeah, and that's a program, right? That's on animation. They actually have a program that is doing that. So that's a Vertex Shader. Rasterized. Then a Fragment Shader is a program that runs on every pixel, and or every fragment. So again, these things don't necessarily correspond to pixels on the screen. You could have you could be doing 4 fragments per pixel if you want, or less if you want. Carmack and Romero, yeah, I've watched a number of Carmack's talks, and that dude just, like, my brain just like explodes every time. It's so cool. Dude is so amazing. My one claim to fame is having traded emails with him a few times. Okay. So shaders pass things to each other. Once they rasterize, you've got pixels, and then you can run shaders on that as well. And then those go into the frame buffer that I was telling you about before. So, all right. So let's take a look at what let's see if I can show you some cool pixel shaders first. Pixel line, that's cool. Just give me some cool shaders here. Yeah. Making it look like an old 80s style game. Yeah, it's alright. There's better stuff. Dynamic 3D pixel art, particle lighting. Math for game developers. That's cool. Really? No good? Just want to show some examples, dude. Oh. Go into shader toy then. Okay, so here's the shader. Alright. And so this is the entire program here. And so what does it do? Alright. So first of all, these things here are called pound defines or hashtag defines. They set constants that control the behavior of the shader. For example, if I was to come in here and change the size of the orb in half, and then where is the thing? Sign in. There you go, compile. You can see how the ball got smaller. Right. And if I compile it again, it's even smaller, right? And so you can do things like mess with the different parameters here and stuff like that. Glow of 0.2 and just kind of mess with them a little bit. Okay, so what is this doing? Let's see if we can break it down. So this is like C, but it's not exactly C. It's its own kind of special shader language. So we got a function here called Kale. I don't know why it's called Kale. Maybe it's the guy's name. I watch these things and forget I need the basics. More the most will ever accomplish. Welcome to D. Yeah. What basics do you think you need to know, Lape? Because this is a basics class. If there's anything you guys want to know that you feel like you need to learn, we got one more class, so I'll be more than happy to teach you whatever you want to learn. So it's a function that takes some parameters and returns a vector 2. A vector 2 is a x and a y. So it takes in an x and a y, an x and a y, and a float, and then it returns a vector 2. So this is doing some sort of trig thing here. Okay. And so this is the program. So the program gets called over and over again, and it gets passed in a coordinate, which is an x and a y location, and it returns a color at that location. So all the shader is doing here is it is repeatedly being given at 100 across, 200 down. Go. Okay, neat. So it takes the coordinate and divides it by the resolution of the screen, and that will give you a times 2 minus 1, and so that will give you, let's see, if we're halfway across, that'll give you 0.5. 0.5 times 2 is 1, minus 1 is, so it's going to put it in what's called screen, screen normalized coordinates, where basically the center part of the screen is 0, the right side is 1, the left side is -1, the top is -1, and the bottom is 1. So this is very common when you're doing this kind of stuff, where rather than using 0, 0 as the top left corner, 0, 0 is the center of the screen, and it ranges from 0 to 1, and 0 to 1, -1, 0 to -1, 0 to 1. And that way you can write your code regardless of the resolution of the screen. It'll just scale to whatever resolution you currently have. Just gonna mess stuff into projects, make it 2D top-down for Unreal projects. Fun. Cool. All right. So the UV, where is UV? That's the screen coordinates basically. The x coordinate is multiplied by the x resolution and divided by the y resolution. So it's doing some sort of like aspect ratio thing here. So if it's at 1, it would get multiplied by like 600 and divided by 400. So yeah, it's scaling based on the aspect ratio. And then the whole thing gets scaled by 2.2. I'm not sure why they do that. Let's find out what happens if we change it to 1. You cannot convert from constant to... Okay. 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 Did something. Okay. So fragment color is a vector 4. So vector 4 is for numbers. And basically all of the numbers in shader worlds are doubles or floats. There, like you saw that like when I tried changing it from like 2 to like an int like that, it doesn't work. Everything's a float. So if you want to have 2, you would do 2.0 like that. And or you can just go to dot. Even though it kind of looks weird to me, that works fine too. Okay, so a vector 4 is just 4 floats hanging out together. The components of them, it's like in Quake C, the components of them are called X, Y, and Z. For vec 3, for vec 4, I think the fourth one is called W. And you can also call them A, B, C, D, and I think there's a third naming system of them too. But if you were to refer to like frag color dot X, like that, this is referring to the X, Y, and Z parts of it. Let's see here. Yeah, like dot X, like that. You could also refer to it as UV dot A, I believe. And vector selection average. What is it? Maybe R. R. That's right. There. And notice how nothing changed, right? Because dot R is the same thing as dot X. So it's RGBA or XYZW. It's the same. It's, you can use it for a color. You can use it for a screen location. If you change it, literally nothing changes in the code. It's the same thing. I wrote a JS demo that's effectively a shader. Cool. What does a shader look like in a 3D world? So all of those materials that we were making in Unreal Engine, those are all shaders. So that's what making a shader looks like in Unreal Engine, right? you take and you're given, well, it looks, I mean, the process of making it looks completely different. Yeah, so you can do things like do bump mapping and all those, interpolations and things like that. All those tricks, it basically compiles down to some sort of source code like this. And so in Unreal Engine, it's just a nice plug and play kind of thing. For your next little minor assignment, which is not going to take you guys very long, I hope, just run through a little tutorial on these shaders, and you'll kind of understand them a little bit better, I think. So fragment color equals 0. The distance is the distance from, okay, so that's the distance from the center of the screen. So this is a variable that is just how far away the current pixel is away from the center of the screen. That's why probably, I don't know, okay. UV, if warp is true, which is true, okay, so it's always true. UV, which is a screen coordinate, times, and then there's some function. And this function is doing the weird, trippy arctan, sine, cosine, whatever. I don't know. I don't understand. I don't understand the trig going on here. We've got some sort of angle, and they're using the angle to do stuff and whatever. And so if we were to comment out the rest of it, if we were to make balls 0, nothing happens. Interesting. Okay. Let's see. Let's make balls 1. So this is the result of Kale. Okay. So Kale is returning. We're just running Kale once, and then and so this is 1 ball. And so the more balls you have, then the more of these streaks will start appearing on the screen. Like that. If you go up to 3 balls, then here. Do 30. It's all white. Anyway, at the end of the day, it's your job to return a color. And so they do all this stuff here, and at the end of the day, it says fragment color, which is the output parameter here, and it does more math, and it basically is going to return the pixel value there. Now, you can do things like you can load textures up into here. Documentation, maybe. Leaf page. Sound shaders, VR shaders. Yeah, there's different inputs you can get. So there's some globals that you can use. For example, time is pretty common, where you use the current time and you can do sine waves and things like that on it. You can get the mouse location, things like that. And there's a tutorial somewhere. Do a password reset, it looks like. Works in Wallpaper Engine. Nice. Oh. Okay. Oh, that's still running. Vertex and Fragment Shaders. Nice. So the point is that you can run this program on every pixel here, and you do cool stuff with it. So for example, you can do cell shading and edge highlighting and things like that. So let's see if I can find the tutorial. Here we go. So I found this nice tutorial for you guys, and let's see, do this. There we go. Okay, so here's a really simple shader. It's a lot simpler than the last one we were looking at, right? And here's another one. See, it's like I was saying a second ago. You can load textures into it, and so this would be how you do it, like in a game, right? You'd have a triangle, you'd have a texture that was on that triangle, you'd have various information, and then you run a program and do things like cell shading, like if the light is between this level and this level, then just flatten it, that kind of stuff. So here we have sine frequency. Let's set the frequency a little bit lower, I guess. Let's see what's going on here. So what's going on here is for every pixel on the screen, it is getting the x and y coordinate. It then divides it by the resolution. So that is going to give you a number from 0 on the left side to 1 on the right side. So this is also a normalized screen coordinate system, except instead of having 0, 0 being in the center, 0, 0 is top left, and it runs to 1 x in the right and 1 y down. It then grabs from the texture here. There's a texture here. It's going to grab the from I channel 0. That's this texture. From 0 to 1, 0 to 1, it's going to grab the pixel at that point. And so it grabs the color of the, like if you pass in 0.5, 0.5, it'll give you whatever color value is exactly halfway in the middle of this texture. And then what it's doing, it is taking the time. Remember, the time is a variable. It's a global you can always use to animate stuff. Multiplying it by the frequency, and then that is going to give you a number from 0. Well, it's going to give you a number from -1 to 1. But if you get a negative number, I think it's just black. Let's maybe make this absolute value, maybe. Let's see if that'll make it look a little brighter. There we go. So when it's in the negative world, it doesn't just go black for a while. Okay. So it's taking the sine of the time, and that ranges now from 0 to 1, 0 to 1, 0 to 1. And so that's just going to brighten and darken the total output. Then we got here, we're grabbing the X color, which is R. Like, to make this more obvious, I can say the red channel is going to get multiplied by how far to the right we are. Oh, it's got mouse. I see. Yeah, look at that. Okay. Yeah, it's got mouse support. Okay. So that's why it was all blue. Okay. So so it multiplies how far we are to the right times what percentage to the right the mouse was. And so if we go all the way to the right, then the red channel is going to be at 100%. And if we go all the way to the left, there's going to be no red left, because if I pass in 0 as the X location, that's 0 divided by anything is 0. So the red channel gets set to 0. The Y, which is the same thing as G, is going to be based on how much down I've clicked. So if I click down here, it's got full green. If I click up here, oh, sorry, I guess up is 1. So up here it's full green, and down here there's no green. And then the blue color always comes through. And then the opposite is 1, so it's always opaque, fully drawn. So what happened if I change that to 0? Nothing, because it doesn't matter. Okay. So that is a shader. So it's grabbing pixels out of an image, and then just using the click location to add in or subtract red, add in or subtract green. You guys understand? Just wanted to make something like simple, on this order of difficulty. Something kind of cool. Ah, so that's how you do it. Are you talking about this thing here, Love? Or when I was talking about Unreal Engine? So here we have another example, and again, this is the coordinate, and this is going to divide by the resolution, and this is actually doing two divisions at the same time. So it's actually taking the coordinate, which is a 2D input, it's x and y, and it's dividing by the resolution x and y. And so it's actually doing two divisions at the same time and saving the results into a 2D vector here. And then it is taking the time, adding it to what? X, Y, X. Oh, that's funny. Yeah. So rather than, so it's making an RGB value where the R value is the X coordinate, the G value is the Y coordinate, and the blue value is the X coordinate. So that's interesting. Time plus that plus 0, 2, 4, and so what's going to happen is that's going to get cosigned if we didn't have this. If we didn't have that, then basically, yeah, we're getting a lot of purple because the red and the blue channels are exactly the same. So when there's no red or blue, all we get are the green, and when red and blue are high, we get purple. And so they add offsets in there to kind of break up the colors a little bit. We do X, then we get grayscale. And so it's just the time plus the coordinate run through cosine. And it is dividing by 2 and adding 0.5 to it. So the smallest value of cosine is -1. -1 times 0.5 is -0.5. Plus 0.5 is 0. Biggest value of cosine is 1 times 0.5. So yeah, this is going to normalize it down to 0 and 1. So we don't need to use absolute value here. And then it is taking the color and just adding an extra an extra 1 to it. Okay. You guys think you can do something along those lines? There is a tutorial, leaf page, and kind of explains what happens. You just kind of run through it and just, I don't know. That's it. That's the whole thing. It's only a couple pages long. Just run through it, do something interesting, post it. You know, it'll hold your hand through it. Yep. So put that on Discord there, and let's see. And then what you're going to do is you're going to paste a link to the shader. I'll just make that do, I don't know, a week's way too much time for that, but whatever, it's fine. It's easy assignment. Okay, so the yep. So that's been put up on to Canvas, and just run through it and just make a little shader. It's fun. I guess I'll fire up Unreal Engine and see if there's anything else inside of there we need to talk about. You guys have any questions about shaders? They're fun. There's a lot of really cool tricks you can do. I attended some talks given by NVIDIA on doing shaders back in the day, and I don't really work with them that much. I pretty much just use the material nodes and things like that. Let's see if there's anything in here that I talk about. Have I ever used Unity for this class? No. I use Unreal Engine because in C++, and I teach C++ for my C++ classes. So it just seems like a more natural fit to me. Still loading. All right, hang on a second now. Some fantastic. Just gonna pause the stream in the meantime. Super fast recording. All right, so this is from last year, and we got our Sentry Gun thing here, and it'll rotate to shoot you. It's also playing sounds as it shoots you. Get it turned off. Got physics turned on this thing here. It's like some Rocket League kind of thing, where you can push this and get a score. Down here I've got some bobbing boxes, and this is solid water for some reason. So you can see here the boxes are all kind of bobbing in the lake, and so I thought I'd talk about that a little bit because it's kind of related to the Vertex Shader thing we just looked at here. And so it's a pretty simple animation. What it's doing is I've got a if you've ever done trig, you know that every wave can be described as an amplitude, frequency, and phase. And so amplitude is how big the sine wave is, and so it's going to bob up and down, higher and higher with more amplitude. Frequency is how quickly it bobs. If you put it to 2, it'll bob twice as fast. It'll go up and down twice as fast. And phase is you can think of it as like sort of the delay before it starts bobbing, although that's not exactly right. Basically, you can have all the boxes bobbing in time with each other, or you can have them bobbing out of phase with each other. And I want them bobbing out of phase with each other because it looks more realistic that way. So what I do is when the box begins, it will randomly pick a number from 0 to 2 pi and put that into the phase. So that will have the boxes all start kind of at a different, like, it's not starting because it's all trig, but you can think of like where the high point is, it will be a different offset from each of them. So every tick, these things are animating using event tick, which is terrible, don't do it, but it's educational, I guess. So what's happening is every time a tick gets called, it's going to set the location of the box equal to their the static mesh component. Yeah, so the static mesh component is going to move up and down relative to the origin of it. So it's going to have an initial position set, and basically it's going to compute an offset from that initial position only in the z direction. So it bobs up and down. It doesn't move left or right. If we wanted, we could add a little bit of roll to it, a little yaw, a little pitch, a little roll, have it kind of bob around a little bit that way. So this is related to the shader. So what we're doing is we're getting the current time, and we add the phase to it, and multiply that by the frequency, and run that through a sine, and multiply that by the amplitude. So if you've taken trig, this would probably make sense to you. If you haven't taken trig, it's magic, and don't worry about it. But basically, by adjusting these 3 parameters, phase, frequency, and amplitude, we can control how big the wave is, how quickly it bobs up and down, and how far apart the different boxes hit the peak. So yeah, so this is kind of a cute little animation. Maybe we can add some yaw, pitch, and roll to it. Maybe that could be fun. Thank you. So I added a reroute node by double clicking on it, and then you can drag the orange box around it to move the reroute node around so it doesn't just go through the other node. Okay, so for this, what we're going to do is let's split it, and so we can give it a roll, a pitch, or a yaw. So roll is this tilting left and right. That's roll. Pitching is pitching up and down like the nose of a plane, and yaw is spinning in place like this. Okay. And so what we could do is let's just start off by just rotating it randomly. It's going to look really bad, but again, whenever we work with these things, you always just want to make sure they work first. You know what I mean? So let's just set the yaw. Let's set all of them to random. So random float and range from 0 to 2 pi. Let's actually just give it a random roll and a random pitch and a random yaw, and this thing's going to look really terrible. That's okay. I just want to make sure that it works. Maybe it's in degrees, which maybe it is. Yeah. You see him twitching. Yeah, like I said, it'll look terrible. All right, so Sun expects radians. Do these expect degrees or not? I don't know. Okay. So what we're going to do is we're going to delete these out, and rather than doing a random, let's do time again. So let's pull time. We'll just pull time through a sine node. Sine and radians. Sure, let's try this. And let's just make it roll. Okay. So let's see how that looks. So while it's playing, you can always have this open here, and you can pause. It's currently at -0.4. Not enough to matter. Stop. So we're going to get a number from negative. Oh, we'd actually just do the same thing here. Actually, what I'm going to do, I'm actually just going to pull the result of this out, feed that into there, and just see. See how that looks. too bad. Not too bad. Could be better. It's not too bad. What do you guys think? See how the boxes are now kind of tilting a little bit one way and a little bit the other way? Yeah? What do you guys think? It's not too bad. Alright, let's try it again just with different offset values. So it looks like two of them got the same phase. Let's see how this looks at different times, different random values. Yeah, it looks a little better. Alright. The yaw looks a little weird, I think. Having it yaw is a little strange. Okay, so let's clean that up here. So I don't think we should do any yawing. And then the roll and the pitch being the same is also a little bit weird. Because it's rolling and pitching at the same time, so it's doing like a 45-degree movement every time. It's a little bit odd. Let's try squaring it to see what that does. Does UE have jello water? No, that's only in Quake C, unfortunately. You could make it yourself. Like if underwater, then yeah. Eek. A little too strong, I think. Bit weird. So it kind of jerks like that. Probably because it was negative and the power is causing it to go positive again. Let's see. Maybe do something like this. They'll be offset by 90 degrees. Yeah, that's actually just going to make it move. It's actually just going to make it move 45 degrees in the other direction, isn't it? Oh. Let's see how that works. Yeah, so a good technique for you guys to remember is time running through some trig function will give you kind of nice, smooth motion. So you can play around, and honestly what I would do is I'd create different constants for the phase, amplitude, and frequency of the roll and the pitch, and do all that math 3 different times so that you can control all of those parameters separately from each other. As it is, this looks pretty good. This looks pretty good. Not perfect, but looks pretty good. Okay, so that's better than before. It was the opposite of the Wix direction. Yeah, it's just random though. It's not actually. It doesn't actually know anything about the water and things like that. So the water itself is just a material. And you see down here where it says base pass shader, you know, base pass vertex shader, you know, and so you've 216 instructions, and so what that's telling you actually is how many lines of code the shader, this material graph that we have here, creates, right? And so you can use that to sort of estimate the GPU cost to using it. The more shaders you have, the more complicated the shaders you have, the bigger the frame rate hit you're going to take, right? Now GPUs are pretty fast, and they're able to run things a lot faster than CPUs, and they can run things in parallel. And so, you know, it's just one of those things you kind of keep an eye on. You know, ooh, that's cool. Huh. Fancy. Right, so it's got a panner, and the panners are sliding the textures around, and the panners are, that's going to be the normal down here, normal intensity, and that's going to feed into the normal map. And so that's all this is computing waves essentially. And they've got high frequency, medium frequency, and low frequency waves that are all adding together, and they're adding together in different combinations. And yeah, all that is just to compute the waves that are on the water. And then it's sampling, I don't know what that is exactly. Oh, a cube map, maybe? Fake specular, I don't know what that is. So that's how much it glows. The diffuse color, light and dark powers. It's got a Fresnel node here, and the diffuse multiplier is 0.08. So that's going to the base color. So the base color is going to be some mixture of that based on the angle of the waves to you and stuff like that. Metallic's always 0. Specular is always 0.25. Roughness is pretty low. It's water. And then world position offset. So that's going to actually add to the apparent height of the world, and so it takes time and multiplies in. That would be frequency, and that would be amplitude, and then it does a bunch of math and takes wave height of 20, multiplies that at the end, and that gives you the offset into the. So it's like a vertex shader also. So it's actually moving it's not just simulating it. It's actually moving the vertices around. And so if we were to look at this, you can see the edge is moving here. So it's not actually a simulated thing like a bump map. A bump map simulates raised areas on a surface. A vertex shader actually moves the vertices around. And so you can see this thing is actually, it's in a sphere shape, so it doesn't really look very good. But now that you guys kind of know what a vertex shader is and a pixel shader, this one's both, right? So it's actually moving the vertices of the water around. And so you can see from up here, we've got, you can actually see waves moving on the surface. And there's higher frequency and lower frequency waves. If you get down close, you can see there's probably even higher frequency stuff on top of it than that. But those things are actually moving, right? Like if you look at where the water intersects the landscape, you can actually see the edges are moving up and down. It's not just a plane like what I had on mine with a panner node on it, with the panner sliding textures around. This one's actually moving the vertices around. So. Looks pretty good. Okay, let's see. And then, of course, there is the new water system, right, which has buoyancy nodes and things like that, so you can actually attach pontoons to objects. And so if you want to actually do buoyancy properly and have the buoyancy interact with the water, if you use the new water system on objects, you can attach pontoons to them. And the pontoons are given a certain amount of buoyancy, in other words, how much they push up. And then that interacts with the physics system, and the physics system will interact with the water and the waves. You can actually have boxes that actually float using the actual waves. There's actually no interaction at all between the box and the water. It's just simulated, right? Like I'm just faking it. But if you use the new Unreal water system, you can actually do that for real. Let's see here. So I'm showing and hiding things over time. I've got here a door. I walk forward, the door slides up, walk out, door slides back. We talked about that before. Scoreboards. Welcome to Fall Ball. Different Quixel items, things like that. These are the same materials, right? Just different texture parameters on them. This, you can see it's simulating like it's simulating bump map, but if you turn sideways, you can see there's actually no depth to any of it, right? It's not a vertex shader, it's a pixel shader. So it's pretending to simulate a little bit of depth on it. It's pretending to look like it comes out of the ground, but it's complete simulation. Whereas with the vertex shaders over here, it's actually moving the vertices around. Okay. We talked about blueprint interactions, right? So like having a point total update. It's like if this guy enters the zone, it's just a zone. So when anything enters the goal zone, it tries casting the thing that entered it into the giant ball blueprint. And if it does, then it plays applause. If it failed, it plays some explosion sound just to show what happens. It then teleports the ball back to the starting location. I would probably do this using a variable rather than just hard coding it. And you can actually take like a point and drop it in the world, which is usually what I do. I showed you guys how to do that before, right? Like, you come over here, and what is it? Target point. So you can actually just put a point in the world like that, and use that as the teleport location. So for example, let's name this. Let's name this point target point. We'll call it ball reset point, like that. And then inside of here, we could either do a find where we're like, let's find every target point in the world and find the one named a ball reset point. We could do it that way. Or we can just create a variable that is a point. Target point. We can make a variable and call this guy reset point. And then in order to make that thing appear, we have to do compile and save and close. And then what we can do is with this goal highlighted here, we can link these two things together by using the eyedrop tool, or we can just click on the click down and choose it, but either way. So eyedrop tool, and then we click on that point right there. And so now this blueprint here is linked to this point. And so you could have multiple goals, and so each goal could have its own ball reset point. So you could have maybe multiple teams, and each time you score, it teleports to some specific point. Or you could hard code it so that all of them would always go to the ball reset point. It's up to you. So now if we do this, oh wait, we haven't actually done anything with it yet. So now when the ball gets teleported back home, what we're going to do is, rather than hard coding this location, what we're going to do is we are going to get location. Actually, what we're going to do is this. We'll just pull out from here, get reset point. Now, let's see. Now, we want to do it automatically. Get world location for the, doesn't matter which point. I hope it doesn't matter. Okay. So compile, save, run. and then it goes to the ball reset point, not where it was before. And so it's really important, especially when you're starting off, is like a lot of people just don't know how to make things talk to each other. Like how do you make, like, you can look up like how do I teleport an object? It's pretty easy to find. But like how do I set a point that something teleports to? How do I connect everything together? That's usually the gap that causes new students in this class the biggest trouble. It's like I kind of know what I have to do, and I kind of know some of the individual pieces, but it's like, how do I link them? How do I, like kind of architecturally, like how do I do it? And there we go. And if I had multiple target points, then I could have it randomly picked from them or something like that. So there could be random places where the ball reappears to. Yeah, it's like what T.S. Eliot said in The Hollow Men, between the intention and the action lies the shadow, right? Like you want to do something, and you kind of know what you have to do, but like there's that gap. Like, and I think T.S. Eliot was talking about motivation. Like a lot of people, like, I want to make a game, but they just have no motivation for it. Or sometimes they have the motivation, but like they get stuck on something. They're like, I don't know how to do this. And then they sort of like, oh, if I can't do it, I can't progress. And then they sort of give up. And so it's really important for you guys to know, you can always just message me at any time, day or night, and I'll help you with it. It's okay. A lot of students are embarrassed. Like, he'll know I don't know how to game program. It's like, I know. That's why you're taking this class. If you're working in the games industry, you'd be speaking at this class, not taking it. So, yeah. So just I would just find your passion for something that you think would be fun, and then if there's architecture, like how do I do this in a game, then just ask me. It's like, what about a scoreboard? What if we change this, get the ball into the goal? What if you change that into the current score? Okay. So let's gravity's really low right now. Okay. So let's do that. We've got like 4 minutes left. It seems easy. Let's turn this into a scoreboard. So what type is this? You are text render actor. Okay. So we're gonna edit the blueprint again, and we are going to create a variable for scoreboard. Make it visible appear out in the world, and we're going to look for a text render text render actor. There we go. Okay, and compile, save, come back out in here, and we can simply drop that tool there. Boom, they're now linked together. Save the world. Da-da. All right, so now when we score, we want to keep track of the points on each team. And there's a couple different places where maybe you should put the points, like maybe in the world blueprint. Maybe the world blueprint should hold how many points we have. For this is the goal. I guess the goal can keep track of it too. So we're going to make a variable here called points, and it is going to be of type integer. And we'll make it public. Why not? I don't really care. Save compile. Points should default to 0, which it does. Okay, so after, oh yeah, and this is messing with the physics engine as well. So after the ball teleports, its physics speed is set back to 0, and its rotation set back to 0. And then we will just do points plus plus. So let's do this and just say points. Do that. Plus increment int. So points is going to increment, and then we are going to set the score on scoreboard. We're going to set scoreboard. No, we're not going to set scoreboard. That's not exactly what we want. To get scoreboard. And we're going to set its string. Set its what's it called? code in here. There is a difference between strings and text in Unreal Engine. Okay, so if we do this. You can see the world now has a 1 floating in the sky. Shift through again. Now has a 2. Right. And so you can have multiple scoreboards. Like you can build a stadium, you can say home team, away team, and just update the scores every time somebody scores. Pretty easy. Okay. That is it for today. If you guys have any requests of things that you would like to learn about on Thursday, let me know. That's our last class together. Games development is a huge area. It's a huge field. I think the shader assignment's gonna be pretty easy for you guys. Just run through the tutorial and just like do a little something and give me the link. That's it. That it should hopefully teach you a little bit about shaders. Just a little taste of them, you know. I can dip back into Quake C, and if there's anything in particular in Quake C you want to see, we can do that. If there's anything in Unreal Engine you want to see, we can do that. So let me know. What do you guys think? It'll be cool. Nothing. Just play a board game together. Teach what a game instance is. Just play diplomacy. Showcase your best game projects. Good. We should play a game. I think we ought to play a game, at least a little bit. Maybe some Jackbox or something. It's the end of the semester. The 4 of you that have remained, you know, have survived. Got Steam working with your project? Nice. Very cool. Yeah. Yeah, maybe Walker, if you want to show off your stuff on Thursday to this class, that could be kind of cool. Might inspire them to take IS50B. Yeah, it'd be cool. All right. So the main topic for today's lecture was shaders. And I gave you a little assignment on shaders where basically you're given a 2D location and you return a pixel at that location. That's all a shader is. And you can read from textures and manipulate things and have if statements and for loops and all that kind of stuff. At the end of the day, you're basically saying that pixel should be red. And that's it. For a pixel shader, a fragment shader. For Vertex Shader, you can do things like move the vertices around for waves and things like that. Or you can do cool animations like crushing a can and stuff like that. With it, you like C++? That's all you knew before the class. Yeah, you do C++ in Unreal Engine. Walker, maybe you want to show your dev environment for Unreal Engine.
I can do that.
I could do that next time, not this time. In IS50B, we've been doing a lot of C++ coding, not actually in Unreal Engine. I was kind of maybe intending to do Unreal Engine. I know Walker wanted Unreal Engine C++ coding, but we've actually been coding kind of a renderer from scratch using the tools of the mathematical tools, cross product and dot product and rasterization and things like that. Click. Yeah, that's rasterizing the wireframe, right? And then having to fill it with colors and things like that. And then last time we made a Wolfenstein client. So you can sort of walk around inside of the world. Doesn't have any textures, so it looks a little weird. But you can, this is rendering inside a putty, right? So this is a terminal. And this was 2 hours of work. So you can WASD to walk around, arrow keys, was it to turn left and right? Yeah, so I can turn left and turn around. I got a wall right in my face. So I'll back up a little bit. strafe right, strafe right, strafe right, strafe right, yeah. Strafe right, turn left, strafe right. Yeah. Yeah, so it's you know, those are the kind of things we did in 50B this semester. I think the students that weren't programmers didn't have as good a time, so I'm gonna have to rethink 50B next semester because it's something I've wanted to do for a while, which was actually to build like a renderer. You know, it's actually really good. It's a really good exercise for students to actually, rather than using an engine, actually kind of work on an engine at least a little bit, so you kind of understand how rasterization works and the rendering pipeline and how to, you know, put things on the screen. You know, physics engines. We did, you know, this thing here, the physics engine sand simulator, essentially snowflake simulator. Do you have a final for this class? No, there's no final. So take it easy. Like I said, just show up on Thursday and you know, play some Jackbox or something. And I would like for you guys just to think about what topics you'd like for me to talk about on Thursday and message me beforehand, because games is so huge. Like, you know, like there's all the sound and music side of things that I've basically not talked about. If you want, I can show how to do some of that stuff in Unreal Engine. It's not too bad. Like how do you start a sound? How do you stop a sound? Attenuation, that kind of stuff. We can do that if you want. Okay, so Walker has his screen sharing. Let's click over to that here. Pop out. I was actually planning on Thursday for this, Walker, but sure. So Walker, you wanna walk us through what you got up on the screen here?
Okay, so this is my game instance, which is something that is created the second you launch the game, and it persists throughout the entire project. It's like a singleton. And I bind different delegates upon when certain events are called. So then if you host a session, it'll look at the subsystem that you're using, which in this case is Steam. It will create the session interface for it, which is actually just a pointer for session, what the session is like. And when it's complete, it'll run through this logic. You always have to get the subsystem and check if it's valid, which I don't really like because I don't like repeating myself, but you have to do that. Call the delegate. If it's successful, then start the session. Then you can start online games. But yeah, we got it to work with Steam. And then the find sessions doesn't work right now. So right now what we have in our game is just a
What does TDPVP mean?
it means top-down PvP game.
Gotcha. Okay.
So it uses my Steam name in the top right, and you see the Steam stuff launches up. Right now, what we're using is just like a server browser. But right now, nothing is. This always pops up. I don't know why. I think it's because I'm setting up logic to when you first join. I want to do like the main menu kind of lobby thing, to where you're like how Overwatch works, how you can invite people from the main menu, and then go and launch button. I can click host a free-for-all game, and now I'm in a game. And then if somebody else had the game, they can open up the server browser, see this session, and join it.
You have a scoreboard? You have a...
Nah, I gotta make that stuff. I've just been working on trying to get all the Steam stuff working.
That's cool. That's really neat. And so maybe if you have something up before class on Thursday, we could all download it and we could stress test your game a little bit.
Yeah, and then I'm trying to make as much as possible in this base character and make it as like I guess full-fledged as possible. So then Muya and like JT, if they want to change things, they can do it just in Blueprint and not have to go into the C++.
Yeah, you want to talk about what the UPROPERTY macro does?
Oh, sure. So UPROPERTY, Unreal Engine has a reflection system to where if I so this U property wraps this F name variable to be exposed to the editor. So what that means, let me compile. So what that means is anything that is declared with the U property is now exposed to the editor. Like the actual editor you guys have been working with now knows that this is actually a thing. So for example, I have this impact template class that I defined, where I define that here, to, can I close this? Close. I made this template to handle different impacts based on the different surfaces it hits and what character is actually firing. And because in the base character, I made it a U property and a subclass of that class. So then any classes basically defined from that can now be seen in editor. So when this launches, I'll show what that actually means if it's launching.
Yeah, mine took like a minute or so to load.
Yeah. I have a Ryzen 9, like 3900X, but Unreal Engine is just so...
I had
Especially
one.
because we're using the source build.
Yeah, I had one line of C++, and it took like a minute to compile it on Visual Studio.
Alright, there we go.
What's wrong with it? Might be IntelliBuild or AmazeBuild or whatever the damn thing is.
They call it Incredible.
Incredibuild,
Yeah, so because I defined it in C++ as an impact effect, now if I go to the effects tab, you can see right here the impact template, BP Murdoch impact effect, which I declared that right here. So now, if I was doing this like a different character, I would be able just to click the drop down and select whatever effect I wanted to be played. Like I can do like this one. Oh god, it's gonna compile shaders. Okay, there we go. 300, that's not that bad.
It's going pretty fast.
Play a new window. So now it plays a different effect when the impact happens.
That's cool.
And that's all because I declared it in C++ to just play an impact effect when it collides with the world. And then I set it up so people who are working with like blueprint stuff can just click the drop down. And I did the same with like the bullets. There's weapon spread and targeting spread. These are all the animations.
Can you show how like where like weapon spread would be in your C++ code?
Sure. Oh god. Get current spread. Go to it. Right here. So what I do? Let's find actually where I first fire. I'm just gonna walk through the firing. Where do I fire? Here we go. Okay. So I set it up to where when you fire, it gets a random seed. Like this is basically like calling srand, but it's a bit more random. Then I get the current spread that the weapon is going to have, which this references that firing data config that is actually just a struct of different
and yeah, that's actually what I was wanting to show. It's like right there where you have the U property.
Yeah.
Weapon spread or whatever. Yeah, so that's what allows that to appear in the Unreal Editor. So Walker, as a C++ programmer, can tag variables to be editable by Muya and Harlan in Unreal Engine, right?
Mm-hmm.
And so do you guys, Haburn, Dahlin, Lave, Ramos, Stafford, do you guys see that? So like you can have somebody working on C++, and the people over in the editor world can actually interface with it. and it's a really weird system, I guess. Walker, is that a fair way of putting it?
Yeah, it takes it. Everybody on the project has to understand what your guys' workflow is going to be.
No, I just mean like the reflection system in general,
Oh yeah,
because
like none of this stuff would be exposed to the editor unless I called the generated ustruct body, which creates a bunch of non-human readable code to expose it to the editor.
and then you've got the U struct above that,
Yeah,
which seems like.
ustruct has to be there, or else the editor doesn't know this is a struct.
And so when I was at CPPCon, I actually had a conversation about this with some of my fellow professors because I said, I'm using Unreal Engine to teach programming, and they were like, except like all these weird macros and things like that. That's not valid C++. You know what I mean? Like that's all weird Unreal Engine specific macro things they do to do reflection because C++ doesn't support reflection.
Mm-hmm.
And I'm like, that's fair, And so I'm like, I will just use blueprints.
Yeah, like this. This last include, which has to be here, it's something that's generated by the engine. All this stuff allows it to allows the editor to know that things are exposed to it, and it's all just a bunch of like macros and stuff. So it's not really valid C++, but it's valid for the engine.
Yeah, it's just a weird system, and you got to tag U meta, and U enum.
Mm-hmm.
Like you just have to tag all of this stuff, and so like I said, my fellow professors sort of took issue with me using Unreal Engine to teach C++, or to teach coding in general, but by just mostly focusing on blueprints, then it sort of if all you do is blueprints, you don't see any of this stuff.
Yep.
And so, like in CSI 1, I've done Unreal Engine in CSI 1, the most basic programming class there is. And
okay, again,
but
trying to find, where's somewhere where let me just, are you going to let me, do you have you don't, let's try get actor location. What, I can't do that? Do I have to?
try world location.
Okay. I wanted to. There we go. Okay, just double click.
Oh, you're double clicking it?
Yeah, I'm trying to show that when you call something just in Blueprint, you're actually calling the C++ equivalent, but it hides all the UE4 C++ stuff from you. It just does it for you.
So it's going to jump into Visual Studio right now?
Yeah, it'll jump into here.
Yeah.
Where is it even declared? Control F. Current document. What I call get actor. Location. Yeah, it just calls this stuff for you.
And you've got all the macro stuff.
All the different types and all the macros exposed and all the meta stuff, which the meta stuff I don't like at all. The meta is a way to override the default functionality of the U function. And it's like, well, why not just make the U function more user-friendly than offering a way to override how you implemented it? But whatever.
Yeah. So you have a function called K2 get actor location, but in blueprints it just appears as get actor location.
Get actor location.
Yeah. So you don't have the Hungarian notation on it.
Yeah, and then all that actually calls is just return get actor location, and then go to definition. In actor, let's go to that one. Which then calls return template get actor location. And let's keep going until we find it.
This is why I hate.
Which then calls the root component get component location, which the root component on characters is actually just a capsule component. Mm-hmm. We're gonna keep going. Go to definition.
Let's go deeper. one more
which
level of
calls get
deception.
component dot transform dot get location, which we're gonna keep going. Go to definition. All this gets called. There it is. There's where you actually get the extra location. The get component transform. Yep, that's it. All that is called when you just call that.
The inception call.
Yes.
Yeah.
Which is why people say C++ is so much faster than Blueprint. But honestly, for most projects, it doesn't really matter. It's also just much nicer for people to understand how the engine works, just visual scripting, than having to deal with all this mess.
Yeah. Yeah, and that's one of the reasons why I don't like deep object hierarchies and things like that. Because with so many different layers of indirection, you can have a bug in one of them, and it's not immediately obvious why things aren't working right. You know what I mean? And you just have to sit there and navigate around, and I don't know.
The one thing I do like about UE4 C++ is it forces you to have one-way dependencies. It literally won't compile if you have a two-way dependency. Whereas in Blueprint, dependencies aren't really a thing. Everything is dependent on everything else. That is one thing I really like about the C++, as it kind of forces a
tree structure.
kind of a good like tree structure on you.
Yeah.
Like I have the base character, and then all previous characters are going to inherit from this base character. Like Murdoch literally just calls fire weapon for his primary. Whereas if I tried to reference, or if I tried to make the base character reliant upon Murdoch, it literally wouldn't compile. Which I actually really like.
Cool. So you got
It does
some
the same
more
with
functions to implement there on Murdoch, it looks like.
Hmm?
You've got more functions to implement there? Or is...
Yeah, these are all, I declared them in base character as just virtual functions, because each character is going to have their own implementation.
Yeah.
And then I'm trying to get the gameplay ability system working, but that is just rough. It's just not documented, as most things are with Unreal Engine.
It's unfortunate.
Yeah, it also forces your modules to have one-way dependencies. So I can go in the build. Build is calling character system, but character system has no idea that TDPVP actually exists, which I like. And projectile. Yeah, C++ is neat. It lets me do all the base functionality, and then Muya and JT can just come in here and literally just click things and change values. And
what are you guys using for your... are you using GitHub or...
yeah, we are using just GitHub, and then I paid for some Git LFS storage because the Paragon stuff is very yeah, so we just use Git, and then I have it set up to when I'm doing Visual Studio stuff, I can just click this little thing down here, and I can see all my changes and push stuff. And then I'm making it like making all of us work on different branches. So like we have the master branch, which is when stuff is finished, it gets pushed there.
Okay.
Done. Right now, because I'm doing like in progress stuff, I'm on my own branch. JT has a branch he's working on. So then when we're done, it's all good. We just push it to the origin, and then we just merge the branches.
Have you ever had any merge conflicts or any note?
Yeah, we had some. We had some because me and Muya tried to edit the same like file without like talking to each other that we were doing that, and that was kind of an issue.
Yeah, in other source control systems, what would happen is it would tell you that Muya has checked out this file, and so you'd get a warning that he was working on it.
Yeah, like if
check it
you were
out,
using
and then he would check it,
before.
maybe poke him and be like, "Hey, check it back in." Oh, sorry, I forgot. I need to check it back in.
I don't know.
But with Git, it doesn't really have a concept of that. Just everybody has their own branch, and then you can merge branches.
Yeah.
But merge conflicts are annoying.
I thought I still had Perforce installed, but I'd show like if I were to check out a file, it would say this user is working on this file.
Mm-hmm.
And then it doesn't allow anybody to actually mess with that file while that person has that file checked out.
Right. That's a classic RCS style source code or repository. It's not necessarily even source code, but like a repository system, which involves checking out and checking in, and who's got a commit bit, who has the rights to actually push things and write to the repository and things like that. And
Yeah.
Git just has a totally different philosophy of
Git has the philosophy of you handle it. We're not going to deal with that.
yeah, make your own branch. It's fine. Who cares? Just duplicate it.
Mm-hmm. And then one thing with Git is you want to have your Git ignore and Git attributes set up.
Mm-hmm.
I was trying to make it to where the binaries and stuff were not.
Like I know what they are, but do you want to explain to the people at home what those things are?
Okay. Your Git ignore basically determines what is going to be checked out for source control and what is not. So like you see, I have intermediate, saved, and derived data cache. Those are things that are local to my system. So there's no reason for me to push it to the origin to then affect JT or Nick. But if I were to just like save, you should see 47 change files. That should change. I guess it's just now just not. But what that actually should do is go into the binaries. That should have now included the Win64 binaries to then just not be ignored. So I'd push all these files to the origin, which just doesn't need to happen because we're all compiling from a source. We're all C++ programmers. So your git ignore just tells Git, which is the actual source control, like I don't.
Do you actually
Git
use
is the.
GitHub Desktop? Or do you just use the integrated?
I use Git Desktop, but then if I'm doing like merge problems, I'll open up Git Bash and then mess with it in here.
Well, like
because this a lot of times takes forever.
The Visual Studio plugin, do you use that?
Yeah, I also will use that. If I'm just doing C++ stuff, I'll just click this and just do it from here.
Mm-hmm. Yeah.
And then I got Muya using this. JT usually is just working on editor stuff because his computer's kind of and it takes forever to build. Yeah, so your git ignore. Yeah, so your git ignore tells Git, which is the actual source control like software, I guess, what it needs to actually be checking out and just like ignoring. Then your Git attributes tells Git how to handle different file types. And so because I'm using UAsset and UMAP files, which are rather large, I marked those with Git LFS, which is just large file storage. So that allows files over 100 megabytes to be pushed to the GitHub actual repository here. So like in content, I have actually a bunch of like Paragon art assets and everything, which are really big, but they're now able to be sent to GitHub because I marked UAsset files and like MP3 files, PNG files with the marker Git LFS.
How much does the LFS storage cost?
I'm spending $10 a month for 100 gigabytes. Let me see. Bring this over here. I'm gonna see how much I've used.
Yeah, those.
In the beginning, because in the beginning I was using a lot, just because we were doing a lot of pushes with assets. Billing and plans. Yeah, so I've used this much so far this week, and it's just $10 for 100 gigabytes.
And they charge you for bandwidth too, huh?
Yeah. I haven't done a lot of big pushes lately, but this goes up very quickly, this bandwidth.
I imagine, yeah.
Like, eventually we're going to push... do I have Epic Games Launcher open? I do.
Yeah, Paragon, like sometimes when... students load up Paragon assets on like the 960s we have in the computer lab. Like they think they're Unreal Engine froze. You know, like it's not responding.
Yeah,
Like just
eventually,
give it an hour.
eventually we're gonna have like this guy added in the Paragon Wraith and everything,
Good luck.
which him alone is like 6 GB, and that's gonna be pushed to GitHub, and it's just because nothing is compressed at all,
Yeah.
and it's just that's why it's important when you package your stuff. Package project, package settings. It's
Compression.
important to do this: create compressed cooked packages.
Yeah.
It significantly like minimizes the size. It'll take your package from like 8 GB to like 300. Like our actual executable. This is 300 GB. It's like
300
the game.
gigabytes.
I mean, no, it's 500 MB.
Okay.
Yeah, then I zipped it to 332 megabytes
Gotcha.
to send to
Gotcha.
people.
Yeah, that's yeah. Um,
When I don't, yeah, I said 300 GB. Yeah, no, it's when I don't compress it and everything, it's more like 8 GB.
yeah, and the reason for that is because when people do game development, you want to have high fidelity stuff. But like sometimes, like with Titanfall 2, like all the audio is uncompressed. So there's like 50 gigs of uncompressed audio
Oh, dude,
pushed
look at
out
this.
to people. You know?
Look at this. 118 GB.
Yeah, I just uninstalled Red Dead Redemption 2 because
I eventually am gonna play it, so it's still there.
yeah,
It's also because they said it's for performance on lower end machines, because
right.
lower end machines can't handle compressed stuff as well.
Lower end machines, the
And it's
118
like,
gigs of SSD space is a bigger issue, honestly.
yeah, and it's like, you know, that they can just not play it.
Yeah. Yeah, you had Titanfall 2 on there too. Yeah, like, pull that back up. Titanfall 2 is like
Yeah,
80
Titanfall 2.
or no, 60? Okay. It got better.
They, yeah, it got bigger. It was around like 40 to 50 GB,
Hmm.
and then it shot up to around like 80, and now it's 63.
Yeah, most of that's
Same
just
with
from the
Rainbow
graphics card.
Six was around 100, because they did a system where all the can I see it on the store page? Yeah, they had a system to where everybody had the Ultra HD texture pack, whether you wanted it or not. It
Yeah,
was
yeah,
just
yeah.
in your files. Everybody had all these different skins and everything, which are like 4K textures, and they had it that way. So then it's just a click of a button whether you want to buy something in the game and everything, and you
Right.
just have it. And it's like, no. How about no?
Yeah, and I guess if other people have it, then you need it so that you can see
Yeah.
their DLC, right?
Mhm.
Yeah, it's it kind of bugs me just how cavalier game developers are with people's hard drives.
There's a video by Racevic. I don't know if you know who he is.
Who's that?
By a guy named Racevic.
Hmm.
Yeah, called Why Games Are Massive.
Why games are massive. Yeah. You know, we're already half an hour over the
Yeah.
we're already half an hour over the thing. But yeah, Walker, if you want to demo your stuff on Thursday, and we can talk more about this then. I don't want to. I don't want to
Yeah,
keep
I got a
this
lot I
episode
had to
for you.
get done by
Yeah,
then.
it'll be cool. So everyone, please give Walker a clap emoji for coming out and showing this stuff to you guys, and appreciate me not making you do C++ this semester. And yeah, hopefully you guys will come back for IS50B if I haven't scared you off too much from the world of game development.
Amy's gonna take 50A this semester.
Nice. In the summertime or fall?
Or in the summertime, yeah. He saw what we were doing. I was like, I should have taken that class.
Yeah.
I was like, you can take it in the summer.
Yeah, I'm sure.
If you
I'm
ever need
sure.
help, I got you.
Yeah, I'm sure you would want to work with them because I don't think you're going to just abandon this at the end of the semester, right?
No, this is something that we want to eventually have on Steam for completely free. Like, no caveats, just to have a portfolio and be like, hey, we understand the Steamworks SDK, which is very well documented,
Nice.
I will say. And just, yeah, we're trying to build a portfolio.
Yeah, get Shammy on, and yeah,
Mhm.
maybe I'll advertise to the 45 students. Dahlin here is a alumni of the computer science program. taking game development right now, and hopefully enjoying it. But yeah, I think it's a good way of just getting more experience building stuff and getting programming or just being creative. I really like this class, and it just baffles me when people drop like. Okay.
I think a lot of people in 50B go and say, "Oh, you mean I actually have to do work and program?" And they just dip.
Once we're back in person, then I don't know.
Oh, I'm completely checked out from just classes in general because of the online. I just
yeah, there's that disconnect between people. So.
Everyone I've talked to is just checked out. There's like, dude, I don't even care anymore.
I don't know. I'm in Japanese going hard, dude. I'm at 97% in Japanese right now. So, JT dropped out though.
JT dropped, yeah. JT's just in 50B right now.
Wow.
He's actually working on the 5M stuff, and then him and a friend are making this system to where when people are streaming on Twitch, their like website is gathering all the chat logs and video and just downloading it to their site.
Okay, so you're doing scraping kind of stuff.
Yeah, it's actually, if I still have the.
Well, let's talk about it on Thursday.
Yeah.
We're still Dolan and Habern and Stafford and Lave are too embarrassed to just talk about because we're still talking. So let's just call it then, and let's just talk about it on Thursday. How about
that? Okay.
Awesome. Thanks, Walker.
Wait a minute. How do I stop streaming? There we go.
But seriously, dude, thank you. I really appreciate it. And I'll see you guys on Thursday.